Section 4.7, Optimization Problems. These are essentially just going to be a few problems, word problems that are related to the ideas of extrema, finding maximum values for a function, finding minimum values for a function, and how we can look at these under the scope of some applications. So first example, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So first of all, how does an example like this relate to calculus? And this is sort of a metaphor for a lot of the problems that you're going to see. You want to think that this is a pretty simple problem, but we want to see some similar things that will help us with future problems. So he wants to maximize the area. Whenever we see find a maximum value, find a minimum, make something the largest, make something the smallest, we want to think of extreme values. And when we're finding extreme values, at some point we're going to need to involve the derivative. If you're going to use the derivative, you need some sort of function to even start with. So some other ideas that we can see is we know that the area of a rectangle is length times width, so we may need that. We're also given that the total amount of fencing is 2,400 feet, which means that the sum of the three sides of the rectangle, since the fourth side is the river, that sum needs to be 2,400. This also relates to the idea of perimeter. So there's a couple of things that might help us with this. If we just want to draw a picture of a rectangle, but for the fourth side, it's just going to be where the river would be. Then maybe label these sides. We can use length and width, so L and W. You could use X and Y. It doesn't really matter, just two different letters that stand for two different dimensions. So if we want, we could use W for width, the smaller side of the rectangle, and L for length. So then from what we were given, the sum of the three sides needs to be 2,400. This means 2 times the width plus one of the lengths is equal to 2,400. And we also would like to maximize the area. And area is just capital A equal length times width. And then think back to some earlier problems that we saw. If you have some formulas and you're going to use the derivative, having the least amount of variables is usually helpful. So in this case, since we have two equations here, two formulas in essence, we can actually put one of them in terms of just one variable, length or width, by just using a different equation. So we can use the perimeter equation, solve for, say, L, and then we can put that into the area equation, and then we just have area in terms of width. Makes it a little bit easier to eventually use the derivative. So length is the same thing as 2,400 minus 2 times W, which means that area can actually be written as a function of width as 2,400, that's the length, times width, which means that area is 2,400 W minus 2W squared. So this means that area is in terms of width. And if we can find the width that gives us the maximum area, then that essentially will help us solve the problem. So we would take the derivative with respect to width, thinking of W as our independent variable. So the derivative with respect to width of both sides, kind of like we would have done in, say, a related rates section. Taking the derivative too early. So this gives us the derivative of A with respect to W is equal to 2,400 minus 4W. So then think back to when we looked at critical values in section 4.1. If I find out where the derivative is equal to 0, that will help me find some maximum or minimum. So setting the derivative equal to 0, that means I have 2400 minus 4w equal to 0, or 4w equal to 2400, or the width is equal to 600. So that means if the width is equal to 600, then the length is equal to 2400 minus 2 times 600, which means that our length would be 2400 minus 1200, or 1200. So a width of 600 feet, length of 1200 feet gives a maximum area and we would just then multiply those two numbers. So 600 times 1200, 720,000 square feet. So now we only found one critical value when W is equal to 600. How would I have known that that would give me the maximum immediately? So I just kind of glossed over that a little bit. But as we go through this section, there's going to be a couple of other things that will pop up that will answer that for us. I could have used the closed interval method, tested out by thinking of, well, what's the domain of this function? So for your length and your width, there are realistic values for our length and our width. Like you wouldn't have 0 for either one of them. Then you wouldn't have a rectangle. And those are also, the length and width are also bounded by what the perimeter is, 2400 feet. Something else though that we could have just noticed is the area function is a quadratic. And that quadratic function opens down. So we already know intuitively that the maximum happens at the vertex, which is exactly what you just found by finding that W is equal to 600. That's the independent variable location of the maximum. But as we go a little bit further on, I'll have some other reasoning for why we know that we could have just taken the 600 as that's where the maximum is going to happen. So here's another example. What is the minimum vertical distance between the parabolas y equal x squared plus 1 and y equal x minus x squared? So here we notice the key word minimum. We want to minimize the distance between the two, so we would want to think of a function for the difference of the two functions. So this should say, we should name a function for the difference of the two functions. So we're going to say let h of x equal the difference of the two functions, and that just means subtract one from the other, and you would get 2x squared minus x plus 1. So first of all, let's take a look at a graph so you can see what it means for there to be a distance between two functions, and then also you can see why I subtracted them the way that I did. So here on Desmos I have two parabolas. The one in red is y equal x squared plus 1, and the one in blue is y equal x minus x squared. So you can see that the red parabola is above the blue parabola. So it makes sense for us to, when I was thinking of the difference, take the top parabola minus the bottom parabola. And then also, as far as vertical distance, it just means if you were to use the same x value, like let's say x equal 1, then you would see that the red graph is at 2, and the blue graph, this is x equal negative 1. The red graph is at 2, and the blue graph is at negative 2, so they would have a vertical distance of 4. If you were to focus on x equal positive 1, you would see that the red graph is up at 2 again, but the blue graph is down at 0, so the distance there would just be 2. So there are different values for that vertical distance. And it seems like where it is the smallest is where they're almost close to each other. So somewhere near the origin, it looks like we have the smallest vertical distance. So now I have the difference between the two functions, the top parabola minus the bottom parabola, and I want to find the minimum of this function. Notice again, this is a quadratic, 2x squared minus x plus 1. So we know it's going to have an absolute minimum. It's just going to be, again, at its vertex. But we can still use everything that we've learned up to this point. We can find the derivative, because not all functions will be quadratics. So h prime of x is equal to 4x minus 1. Critical points are where this derivative is equal to 0 or undefined. Of course, this is a linear function for the derivative, so it's always defined. So we just set the derivative equal to 0, and that tells us 4x minus 1 equals 0. So x is equal to 1/4. Just like we suspected by looking at the graph, we should expect to see the minimum happen somewhere near the origin. So we found our critical point. To give a little bit more explanation, again, to how I know that this is going to be a minimum, let's just use what we saw in earlier sections, a little chart. And I'm just splitting up the number line with x equal to 1/4. And I just want to look at what's happening to my derivative, which then goes back to saying something about my original function. I can use some test points, x equals 0, x equal 1. When I plug in 0 to my derivative, I get 0 minus 1, which is a negative. When I plug in 1 to my derivative, I get 4 minus 1, which is 3, which is a positive. So our original function, the vertical distance, is decreasing. But then once it crosses over x equal to 1/4, it changes to increasing. And I can see that I get a minimum value at x equal 1/4. So then we are asked to find the minimum distance between the two parabolas. So it happens at x equal 1/4. Since I have my function h of x describing the distance, the answer, the minimum distance, would just be taking our h of x function and plugging 1/4 into that. So 2 times 1/4 squared minus 1/4 plus 1. 1/4 squared is 1/16 times 2 is 1/8 minus 1/4, which is the same thing as 2/8, plus 1, which is the same thing as 8 over 8. So that gives me 7/8. So 7/8 is the minimum distance between those two functions. So now to sort of summarize what we've seen with these last two problems and how I was using a little bit of intuition and even some previous concepts like this chart for figuring out when I get a minimum, we have what's called the first derivative test for absolute extreme values. Suppose that c is a critical number of a continuous function f defined on an interval. Part A, if f prime of x is greater than 0 for all x less than c, and f prime of x is less than 0 for all x greater than c, then f of c is the absolute maximum value of f. Part B, if the derivative f prime of x is less than 0 for all x less than c, and f prime of x is greater than 0 for all x greater than c, then f of c is the absolute minimum value of f. And in fact, this is what we had in the previous example. We had that our derivative was negative, and notice this is for all real numbers that are less than x equal to 1/4, and then the derivative was positive for all real numbers greater than x equal to 1/4. So that's how I knew that not only did I get a minimum, it was the absolute minimum. So let's take a look at another example where we can keep all of this in mind to finish up this section. A man launches his boat from point A on a bank of a straight river 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. He could row his boat directly across the river to point C and then run to point B, or he could row directly to B, or he could row to some point D between C and B and then run to B. If he can row 6 kilometers per hour and run 8 kilometers per hour, where should he land to reach B as soon as possible? We assume that the speed of the water is negligible compared to how fast he can row. Now, if you read that whole paragraph and weren't confused, then I applaud you. Because when I read that paragraph, my eyes start to cross and I immediately think I need to draw a picture just to even see what they mean with A, B, C, and D. So, how about this? This vertical line represents one side of the river, and let's say that this is point A. And then the river is 3 kilometers wide, so let's say that that's 3 kilometers. And if I was to just go straight across, they said if he rowed straight across the river, that would reach point C. So here's C, and that's 3 kilometers across. And they said if he rowed straight across to point C, he'd then have to run down to point B, and that would be the destination. So B would be down here. They also said he could just row directly to point B. And then they also said he could just row to some point D, let's say here, somewhere between C and B, and then run straight down to B. And so we're actually going to focus on this point D, because the thing with these points is wherever D is, D could be C, D could be B, or it could be some point in between those two. So we're going to really pick on point D. So I'm going to label a couple of other things here. I'm going to say the distance from point A to point D, I'm going to call that lowercase d for distance. I'm also going to say that the distance between point C and D is x, so some amount of kilometers that I don't know. While I'm at it in this picture, I'm also going to notice that the distance from C to B, they said that that was 8 kilometers because they said it was 8 kilometers downstream on the opposite bank, which means I can fill out one more piece of this, the distance between D and B. Just think it would have to use subtraction, the greater distance 8 minus the smaller distance x. And then one final thing, it looks like I've got a triangle here with A, C, and D. Why don't we just go ahead and notice that that's a right angle. Okay, now that I've got those things labeled, let's take a look at these bullet points that I wrote down here. We want to minimize his time. So we need to think of some function for time. Since distance is equal to rate times time, you might remember that from algebra, d equals r times t, we can think of the following. The time spent rowing would be just whatever that distance is for rowing divided by the rate of speed for rowing. So time spent rowing is distance rowing divided by 6 kilometers per hour. So I'm actually going to say this, the time for rowing is the distance that the person will row, which is d, divided by 6 kilometers per hour. And I'm just going to use 6. The time spent running is the distance that was run. So the time spent running, that will be the distance that was ran divided by 8. So now, if we're just thinking of landing somewhere at point D, the distance that this person's going to run is the 8 minus x. And so we take that distance, 8 minus x, and divide by 8. So then the total time spent doing this whole exercise activity would be the sum of those 2 times that I just wrote down. So I'll say t for time is equal to, and I'm actually going to use a capital T for time, is equal to d over 6 plus 8 minus x divided by 8. Okay, so now we've got a formula that relates the time with the distances. So notice here I have 3 variables, capital T, d, and x. If you remember from the first example, things become a little bit easier if I have the least amount of variables as possible. So to simplify, I'm going to go back to my triangle that I had up there, and I'm going to notice that it relates d and x together. And so I'm going to use that triangle to get d in terms of x. So I'm going to simplify by getting d in terms of x. So how would I do that? If this is a right triangle, then I have 3 squared plus x squared equals d squared. So I'm going to use that. So 3 squared plus x squared equals d squared. That means 9 plus x squared. And if I take the square root, that gives me d. So time, capital T, is really just the square root of 9 plus x squared divided by 6 plus 8 minus x divided by 8. And here what I want to notice is that t is a function of x, which is saying that the time it takes him to do this depends on what is the value of x, which makes sense. In the whole problem, the time for doing this whole thing just depends on where is the location of this point D. So now we're going to use a common theme from the last couple of examples. Take the derivative, but we're going to take the derivative not with respect to time that we've seen in some problems, but with respect to x, because x is the independent variable here. So the derivative with respect to x of capital T is what we want to do to find our critical points. And then we'll have to do that on the right-hand side. So then d capital T dx. For the first fraction, I can factor out the 1/6 as a constant. The derivative of the square root involves the chain rule, so that would be 1/2 times 9 plus x squared to the negative 1/2, as we've seen before, but then times the derivative of what's inside, and the derivative of 9 plus x squared is 2x. And then the derivative of the second fraction, that's really just a linear expression. You could rewrite that as 1 minus 1/8 x. And the derivative of a linear function is just the slope. So it's minus 1/8. And I shouldn't forget that the big parentheses end right there. So then I can simplify this a little bit. The 1/2 will get multiplied by the 2. And I can rewrite things just using some simple fractions. So dt dx is equal to x over 6 times the square root of 9 plus x squared, and then minus 1/8. So there's our derivative. Now we need some critical points. So critical points, remember, they have to be values in the domain of the function where the derivative is equal to 0 or the derivative is undefined. So can the derivative be undefined? It's got a fraction, and fractions are undefined where the denominator is equal to 0, which means we would be concerned about 9 plus x squared being equal to 0. But that wouldn't happen because 9 plus x squared is always positive. So we don't have to worry about the derivative being undefined. So our only real concern is, where is the derivative equal to 0? So t prime equal to 0, that happens when x over 6 times the square root of 9 plus x squared minus 1/8 is equal to 0. And don't be too hasty with this. You can't just say x is equal to 0, because I've got this constant of negative 1/8. So I actually have to simplify this and try to solve it like an algebraic equation. So I'm going to first add the 1/8 to both sides. And after doing that, I'm going to cross multiply, essentially. Really, I'm going to multiply both sides by the denominator that's on the left. So I'm going to say x is equal to 6 times the square root of 9 plus x squared divided by 8. And while I'm at it, I'll simplify 6 over 8 as 3 over 4. And then what I'm going to do next, if I have x equal to 3 times the square root of 9 plus x squared divided by 4, I want to get rid of that square root, which means squaring both sides, which gives me an x squared on the left equal, and this is going to be a 9 over 16 times 9 plus x squared. And you can start to see how we're almost there at getting an answer. I just want to get x by itself, really, at this point. So distributing, x squared equals 81 over 16 plus 9 over 16 x squared. I'm going to subtract 9/16 x squared from both sides. So I have 1 times x squared minus 9/16 times x squared. Instead of writing 1 is the same thing as 16 over 16. So 16 over 16 minus 9 over 16, that's 7 over 16. So 7 over 16 x squared is equal to, and I had 81 over 16 before. Multiplying both sides by the reciprocal of 7 over 16 gives me x squared equal to 81 over 7. And then finally, take the square root. X is equal to plus or minus the square root of 81 over 7. Now, when we think about those two solutions, if we were to say that they were both critical points, they would have to be in the domain of the original function. If you go all the way back to our picture, would it make sense for x to be a negative number? If x was a negative number, it means that point D would be behind point C. That doesn't really make any sense. So the only critical point that we're going to actually consider is the positive square root. So x equal positive square root of 81 over 7. And again, I can rewrite this as 9 for the square root of 81 divided by the square root of 7. That is the only realistic critical point. So, now that I've got my one critical point, let's use that first derivative test for absolute extreme values that I just talked about. I'm going to go back a little bit more so I can reuse the other side of the page. I'm going to have a number line. Our x values are only going between 0 and 8, and it's somewhere in between, which is 9 over the square root of 7, something a little bit more than 3. And I want to look at what happens to my derivative, t prime, in those two intervals that are sitting right there. So I'll choose a test point, like 1 and 4. If you plug in 1 to the derivative, remember the derivative is sitting right here, I get 1 over 6 times the square root of 10. So 1 over 6 times the square root of 10 minus 1/8. If you were to subtract those, you would see that you get a negative. So this is less than 0. On the other hand, if I take 4 and plug that into my derivative, I would get 4 over 6 times the square root of 25, or 30, minus 1/8, and that's going to be positive. So what I notice here is that I have negative for one part and then positive for the other part. And at that sign change, those are the only things that are going to occur with these critical numbers. That means I get an absolute minimum at x equal 9 divided by the square root of 7. Okay, you could also use the closed interval method to go all the way back to the beginning of chapter 4. And you could just verify this in another way. So it's not like one is better than the other. Maybe one might be saving you some time. But if you were to plug these in, you would get 1.5 for the number of hours it would take if he just rode straight across. If he rode all the way to point B, so no running involved, this would end up being 1.42 hours. And so now let's actually just calculate what he gets for 9 over the square root of 7 as his time for going somewhere between points C and B. So our original function is what we need to use here. So square root of 9 plus x squared divided by 6 plus 8 minus x over 8. So t of 9 divided by the square root of 7, that equals square root of 81 over 7 plus 9 divided by 6 plus 8 minus 9 divided by the square root of 7 over 8. And we're going to get approximately 1.33 hours. So closed interval method or this first derivative test for absolute extreme values will still lead us to the same correct answer. And so the final answer to the problem, thinking back to the directions which say, where should he land to reach point B as soon as possible? That was just the location of D, which means it should be that 9 divided by the square root of 7 kilometers. So we could say as our answer, 9 divided by the square root of 7 kilometers downstream. So the next hardest thing that he has to figure out is, how do you measure that when you're rowing across a river? But that's his problem and not ours. And that's it.